to Wang. He got his master degree from Northwestern Technical University in China. He majored in flight vehicle design. And now he is in his second year PhD in the Department of Precision and Microsystem Engineering in the Delft University of Technology. And his research topic is the design and optimization of wings for a flapping wing micro air vehicle. Supervisors Fred van Keulen and Hans Goossens.
Hello? Okay, it works. Well, thanks for introduction. Today I'm going to talk about the study of design parameters of flapping wings. Well, I'd like to start with these three insects. These three insects, apparently they have quite a different wing morphology, and they also fly in quite different ways. Indeed, studies show that the pitching motion can be achieved passively with the help of the aerodynamic forces and the wing inertia, as well as the flexibility of the wing. So this passive pitching mechanism builds a relationship between the wing morphology and flapping kinematics, and this inspires us to study those morphologic parameter and the kinematics parameter simultaneously to help us design better wings for flapping wing micro vehicle, and to help us understand the diversity of insect wing morphology. Well, this presentation is outlined as, well, the first part is the overview of design parameters, which include the morphological parameter and the kinematic parameters. The second part is the analysis of these design parameters, which includes the importance analysis, optimization, and sensitivity analysis. At the end, I will introduce the conclusion and outlook. Okay, before I introduce the main content, three assumptions should be introduced first. First, the flexible insect wings are represented by a combination of rigid wing and the torsional spring. And the wing membrane-like wing structure is instead by a plate with uniform mass distribution. The third assumption is that the pitching axis of insect wing, which is not very clear. Here we assume the line between the wing rod to the wing tip as the pitching axis. Well, we use 5 morphological parameters to describe such a wing shape. The first two are the wingspan and the aspect ratio. With these two, we can determine the wing area. We use this normalized horizontal position of the centroid to quantify the horizontal, the wing area distribution in the span-wise. But now we still can move the wing area up and down. So we introduce this parameter, the normalized distance between the leading edge and the pitching axis, to describe the chord-wise area distribution. Here we further assume this parameter is a linearly changing from the wing rod to the wing tip. So it can be represented by these two parameters, the normalized distance at the wing rod and at the wing tip. So if these 5 parameters can describe different kinds of wing shape, it can be shown here with different values of these parameters. All these 3 wings are prescribed quite well. The R is not shown here is because I only scale the wing size. So besides the morphologic parameters, the kinematic parameter is also very important. This example of a 3D motion of flapping wing, which with edge-shape wingtip trajectory. We usually use three Euler angles to describe this kind of spatial movement. The first one is used to describe the heavy motion, which denotes the backhand force movement. This motion is described by this function, well, which is quantified by the amplitudes, the parameter k, and the phase shift, as well as the shift of the horizontal position of the horizontal plane. And the parameter k here is used to control the shape function. When the k is close to 0, we got a harmonic shape. When it gets close to 0, getting close to 1, we get a triangle shape. We use this function to represent the out-plane motion. And the 5 parameters are included here, which are the heavy amplitudes, the parameter n, flapping frequency, phase shift, and the vertical position shift. The parameter n here is used to control the shape of the wingtip trajectory. In this work, we use the n equals to 2 with a H-shape trajectory. As to the pitch motion, here we describe this one as a fully passive motion, which is determined by this equation of motion. From this equation, we can find it's determined by 4 parts. The first one is the exciting torque due to the inertia from the wing sweeping motion and heavy motion. The second term is the moment inertia, which includes 2 parts. The first is the wing moment inertia and the virtual moment inertia, which is due to the added mass. And the third term is the spring stiffness. The fourth term is the aerodynamic damping torque. This part is calculated by a quasi-steady aerodynamic model. In this model, we use this model to predict the lift, torque, and power. This model is decomposed into 4 components. The first is the force and torque due to the translational velocity, and the second term is due to the rotational velocity. The third term is the coupling between the first 2 terms, and the fourth term is the added mass effect, which is due to the acceleration of the wing. Well, so now we have 5 morphological parameters and 8 kinematic parameters, as well as 1 spring stiffness. The method we use to study this parameter is to do optimization to get an optimal combination of kinematic and morphological parameters. But it's not trifle to study all these parameters in an optimization model. What we do here is to use importance analysis to find the most influential parameters and to get rid of those less important parameters temporarily, and to make the optimization to be more manageable. The approach we used here is a 5-level fractional factorial experimental design. Well, this is the result of the importance analysis. The first row is the lift with respect to different parameters, and the second row is the power. Well, to make it clear, I classified into 3 groups. The first 5 is the morphological parameter, and the last 7 is the kinematic parameter. Apparently, these 6 parameters show a relatively high influence on both on the lift and the power. However, the wingspan is usually proportional to the body length, so it's usually predetermined. So these 5 parameters are selected as design variables. The horizontal position shift of the sweeping motion and the heavy motion, these three parameters, are ignored temporarily in the optimization. The rest four are prescribed in the optimization. And the prescribed condition is referred to the adult hawk moth with a 5 centimeter span, and the normalized horizontal position of centroid is equal to 0.45, and the sweeping motion is assumed to be harmonic. Here, the sweeping amplitudes are assumed to, we studied three separate sweeping amplitudes: 45 degree, 6 degree, and 90 degree. The objective of this optimization is to minimize the power consumption. Here, two power consumption patterns are considered here. The first one is the driving system is elastic system, can absorb the extra kinetic energy, which can be explained like this: the power in flapping motion, the driving system has to supply power to accelerate the wind and to overcome the aerodynamic drag in the first half of half stroke, and then the kinetic power can be used to transform to overcome the drag. If the kinetic power is much more than needed to overcome the drag in the second half, then this power can be either dissipated or stored by the elastic system. And this is the first case. If the extra kinetic power cannot be stored, then in this case, zero elastic storage. But in reality, the power consumption is in between. This optimization is constrained by at least 1 gram lift generation for single one. So now we have three separate sweeping amplitudes and 2 cases of power consumption. So in total, we have 6 cases. To illustrate the optimization results, I will show the first case with a 45-degree sweeping amplitude and the perfect elastic storage power patterns as example. This is the optimal result, and it can be seen here. The aspect ratio is selected as the minimum one, and the pitching axis is between the leading edge and the center line. If we compare the cases with the same sweeping amplitude but different power consumption pattern, we can find a slight difference of the optimal wind shape as shown here. More area are put in front of the pitching axis if the energy can be stored. For different sweeping amplitudes, I will compare the results from the kinematics perspective to morphology and the power stiffness perspective. So at first beginning, a similar result was got for different sweeping amplitudes. You can hear a curved leading edge was obtained, and the pitching axis is between the curved leading edge and the center line. As to the power, if we increase the sweeping amplitudes, it can be found for both power consumption patterns, the power increase. And for the kinematics parameters, with the increase of the sweeping amplitude, the frequency decreases with the sweeping amplitude. But the optimal passive pitching amplitude increase a little bit if we increase the sweeping amplitude. As to the spring stiffness K, there is a trend of decreasing, which can be explained by that for smaller sweeping amplitudes, we need a higher flapping frequency to achieve sufficient lift. At the same time, higher wind inertia are generated, so we need a stiffer spring to resist that. Okay, so now we have shown the optimization result, but only 5 variables are selected in the optimization. So we still are interested on the other parameters. Of course, we also curious about what's happened to the lift when the design achieves the minimal power consumption. We studied the sensitivity. We plot the result like this. From the result, it can be found the optimal design corresponding to minimal lift is approximately corresponding to the maximum lift. And for the other parameters, the influence to the lift and the power will be classified into 2 groups. The first is the effect of morphological parameter to the lift and power. Well, the result shows that lift is sensitive to all the morphological parameters shown here, but the power is relatively more sensitive to wingspan, aspect ratio, and the pitching axis. As to the effect of kinematics parameter to the lift and the power, the result shows that both lift and the power are more sensitive to the flapping frequency F and heavy motion. If the shape function of sweep motion is getting close to the triangle 1, then it becomes very sensitive to this value. However, both the lift and power are irrelevant to the horizontal position shift of the sweeping motion. It's time to get a conclusion. Well, the overall conclusion can be shown by this figure. We got an optimal combination of morphology and kinematics similar to a butterfly. From the perspective of the optimal wind shapes, we got a smaller aspect ratio, and a pitching axis is located between the leading edge and the center line. As to the optimal flapping kinematics, results show that higher flapping frequency and spring stiffness are obtained for smaller sweeping amplitude, and the optimal pitching amplitude is located between 45 degrees and 60 degrees. As to the power consumption, smaller sweeping amplitude shows smaller power consumption for both cases. But it should be mentioned that it's still difficult to generalize this conclusion for different insect wing size, and optimization is probably necessary for specific cases. Well, in the future, the forward flight and maneuvering will be considered when we study the effects of these design parameters on the morphological parameter and kinematic parameters. And the future optimization will include the wind torsion. Since wind torsion is existing in nature winds, it could be a more energy efficient way for insect flight. Okay, before I end my presentation, I should mention that there are small error in the numbers which given in the flash disk. Please refer to the online version which has been corrected. Well, thanks for your attention. Thanks.
Thank you very much for your presentation, and would like to ask if there are questions, but the first one.
I have two questions. First question, the real wing is flexible, so how the deformation affect your morphology parameter? That's the first question. Second question, the butterfly, some species has a tail or a streamer. Again, how it integrates into your model?
Can you repeat your first question?
Wing is flexible.
Yeah.
So it looks, my impression is like it's a fixed geometry and the wing cannot change shape for your model.
Okay, thanks for your question. So your first question is, how can I replace a flexible one with a rigid one? The second one is, there exists a lot of different butterfly wing morphology. Okay. As to the first question, I would say the flexibility of the insect wing can be modeled, but the energy efficiency will change a little bit, not so high. So here we represent the wing flexibility with a rigid plate with a torsional spring. This can give us at least a trend about the effect of these parameters on the lift and power. As I said, in the future's work, the wind torsion will be included. If we include the wind torsion, actually, that's a better representation, a better represent of the wing flexibility. As the second question, yeah, there are different shape for butterfly wings. So here, I didn't intend to. I can explain why the butterfly wing is like that. It just shows that okay, this is optimal. So at least we can explain that with this result. Is that your answer? Thanks.
In your optimization, you assume the wing motion, which is, let's say, typical for a bee, but because of the optimization, gives you a wing which looks like the wing of a butterfly.
Mm-hmm.
But butterflies, they use slightly different wing kinematics than bees, I would say. Can you comment on that?
Yeah, here I didn't specify the kinematics. So the flapping frequency can be changed, and the changing of the torsional spring stiffness can result in different pitch motion. Well, the wing morphology I used the example is just example.
But still, when the wing flaps in the stroke plane, so the nominal position is, let's say, the wing is perpendicular to the stroke plane, right?
Mm-hmm.
Well, in a butterfly, as I think it is, the wing is parallel to what we would call a plane.
Well, there are some butterflies which is good at hovering, and if the butterfly hovering conduct a hovering flight, and it doesn't matter whether the stroke plane is horizontal or inclined, we can tilt it.
Hi. Thanks for your presentation. The question I want to ask, in your initial design, you used the quasi-steady aerodynamic model to estimate the force and power.
Yeah.
And you consider the transition, rotation, clear coupling, and also added the mass.
Yeah.
But in some cases, for flapping wing, the unsteady aerodynamics really predominated the aerodynamic force generation.
Yeah.
Like the wing capture, the shading, and the generation of the vortexes. So, have you ever considered the accuracy of that quality steady model?
Yeah, we have compared our model with some cases, but we didn't show it here. As to the unsteady effect, that part was included in the they're included here, actually, I would say.
The first second one.
Yep.
Do you have a force profile during each blocking cycle? I mean?
Yeah. But the details was not shown in the paper. So this paper is only focused on the effect of these parameters on heat and power.
So have already compared with experimental data, not linear stop equation.
Yeah.
Any more question?
What is the aerodynamic model? How you estimate the CL and CD of the unit?
Well, first, both the lift and I would say the aerodynamic forces are first calculated in this rotating frame, and then transformed to the inertia frame.
CL and CD for the wind session, you have to calculate the force on the wind session, and then you integrate on the wind to have the lift, right? But in your model, how to
Sorry, can you repeat?
yeah, for estimation, you have lift coefficient for one session, and then you integrate on the wind to have the lift. But my question is the CL and CD of the wind. How you get it?
Okay. Thanks for the question. Well, the lift and drag coefficient here we used the model proposed by we used the analytical model which proposed by which published in a paper recently, which give a very good prediction on the lift and the drag coefficient if we compare to the result which was measured on real mechanical winds.
Reference paper.
Yeah. It's that coefficient is used in this part.
May I have a question for you?
Yeah.
In nature, we see a lot of different wing shapes and motions.
Yeah.
With your method, could you quantify the power that different insects need, and if could you say that some insect needs more power to fly than the other, and does that correspond to their behavior of getting their sugars or what they need?
Well, I think it's not easy, but for some insects which fly with a very high flapping frequency, they usually use a resonant driving system driving their wing. So that means this kind of mechanism is try to minimize the power. If they can combine with the optimal flapping kinematics, I guess their power consumption shouldn't be very lot, I would say. But I can't give a a conclusion from this work.
You could not, from this work, say, for example, a bumblebee is in theory more efficient than a dragonfly.
No, I never done that.
It would be interesting for
Yeah,
future,
that sounds
for any of
interesting.
you, for future work, to test these kind of methods and apply them to some real life situations. Maybe we'll see that next year or the year after.
I hope so.
Okay,
Thanks.
thank you. That basically concludes this